In this video, we will begin discussing the techniques that are necessary to evaluate trigonometric integrals of the forms given here: sine to a power, cosine to a power, tangent to a power, secant to a power, cotangent to a power times cosecant to a power. Now in this video, we are going to concentrate specifically on integrals of the form sine to a power times cosine to a power. And note that one of those powers could be 0, so that it's really just sine to a power or cosine to a power. And as we'll see in our next video, the techniques that we use to anti-differentiate a tangent to a power times secant to a power apply exactly to cotangent and cosecant. Now, in order to evaluate these trigonometric integrals, there are going to be a few trig identities that we absolutely need to recall. The first would be the Pythagorean identities. So I've given the Pythagorean identity that we are most likely to remember. Cosine squared plus sine squared equals 1. But let me remind you that there are two other corresponding Pythagorean identities. And we get those by just manipulating the original. So for example, we could just go ahead and divide each and every term by cosine squared. And if you divide every term by cosine squared, you get the resulting identity, 1 plus tangent squared is equal to secant squared. Similarly, you could instead divide each term by sine squared. So if you divided each term by sine squared, you would have cotangent squared plus 1 is cosecant squared. So also cotangent plus 1 is cosecant squared. And just keep in mind that you don't have to memorize these three Pythagorean identities. If you remember this original one, cosine squared plus sine squared is 1, you can easily manipulate to get the remaining two. Also, the half angle formulas are going to be absolutely necessary. And the reason they're going to be absolutely necessary is a common integral that we might encounter would be something like sine squared. And the most efficient way to integrate this is to simply rewrite in terms of that half angle formula. Though I will note as a side note, it's not nearly as efficient, but you could also integrate this using integration by parts. So let's move on and talk about how we can evaluate integrals involving sine and cosine to a power. That is, what are the standard techniques? And the standard techniques are described here, and I know it's a ton of information, but let me just break it down for you as efficiently as possible, and then we'll see it very nicely illustrated with a few examples. So if the power of sine or cosine is odd, it doesn't matter which one, the technique you use is exactly the same. So if it's cosine, which is an odd power, what you do is you take one of those powers of cosine and you save it, because what that's going to hopefully end up being is your du. And then the remaining cosines, there's 2k of them, you rewrite with the Pythagorean identity. Cosine squared is 1 minus sine squared. And when you have all sines and one cosine, we can let u be equal to sine so that our du is cosine x dx. So regardless of whether it's sine or cosine that has an odd power, save one of them, write the remaining even power in terms of the other trig function. And we'll see this immediately here in an example, but first let me also note that if both sine and cosine have even powers, then you use the previously mentioned half angle formulas to rewrite and then evaluate the integral. So let's evaluate the integral of cosine cubed times sine squared. And we are going to exactly follow the guidelines on the previous slide. And those guidelines said whatever power is odd, here it's cosine, you take one of those cosines and you save that. So I'm going to write this as cosine squared, and I'm going to put the other cosine at the end because I'm saving it to be my du. And then you have sine squared. Then you take those leftover even number of cosines and you rewrite them in terms of sine using the Pythagorean identity. So cosine squared is 1 minus sine squared. And now that we have done this, we are in an ideal situation to use a substitution. We can let each sine become a u, so that du would very nicely be this one leftover cosine, which we have very conveniently saved. So this becomes the integral of 1 minus u squared times u squared du. And the really nice thing here is, regardless of the form, with it being an odd power of cosine or sine, if you go through this method and we do a substitution, what's going to result is just powers of u, which is the ideal situation for us. So with just powers of u, and note we should really have our equal sign at each step, we can take the u squared and distribute it through, and this becomes the indefinite integral of u squared minus u to the fourth. Anti-differentiate term by term, 1/3 u cubed minus 1/5 u to the fifth plus c. And then lastly, we just go ahead and we resubstitute. Each of the u's get replaced with a sign. So this becomes 1/3 sine cubed minus 1/5 sine to the fifth plus c. And the really nice observation to make here is that there is absolutely nothing special about this integrand, except for the fact that cosine had an odd power. If it had instead been cosine to the 9th power times sine to the 200th power, we would approach this in exactly the same way. What would change is just later on we would have different powers that we would have to deal with algebraically. So let's look at one more example involving powers of sine and cosine. Let's look at cosine squared. Because it's only even powers present, we need to rewrite in terms of our half-angle formulas. So I'm just going to go ahead and rewrite. So in terms of the half-angle formulas, cosine squared is 1/2 times the quantity 1 plus cosine of 2x. So 1/2 is a constant. We can pull that out front. And then what remains is, I'll rewrite it, the integral of 1 plus cosine 2x. And individually, each of these functions, the 1 and the cosine 2x, are things we can hopefully anti-differentiate quite efficiently. The antiderivative of 1 is just x. And the antiderivative of cosine 2x you can tell me by inspection, or you could use a substitution. So by inspection, I'm going to say this antiderivative is 1/2 sine of 2x. And if you didn't see this based solely upon inspection, you could always do a substitution. So we could simply let u be equal to 2x and evaluate the antiderivative of cosine 2x that way. So as a recap, if the power of sine or cosine is odd, we have a very nice approach we can use to evaluate the integral. If all the powers are even, something like just cosine squared, or it could be cosine squared times sine squared, as you will see on future assignments, you rewrite in terms of the half-angle formulas, and then you evaluate those resulting integrals.